right, 16.4 triple integrals in application. So we're going to add a third integral to the already double integrals. That's all it is about. But the applications, again, we will have a look at when does a triple integral represents a volume, what does a triple integral represent when you have some f of x, y, z? Well, we'll see about it. So, well, the most generic form. This is how they look like. You have a triple integral over a solid domain. Typically we call it D, sometimes we call it Q. And you may or may not have a function f of x or well, yes, you will always have, because if you only have a 1, that's technically a function. You know, it's a horizontal line, y equals a 1, or vertical, or whatever it is. But well, let's have a look at the structure of this triple integral. So, keep in mind that again, we'll go inside out. This dz right here will be related to these limits of integration. That, check this out. See these limits of integration are functions of the two variables that are on the two outermost differential or the two outermost integrals. So for the innermost integrals, we may have functions of one of each of the variables, x or y or both, or simply numbers, simply constants. Number 2, dy, which is related to the middle limits of integration. Well, so how many variables are left? Just one, x. You see how these limits of integration are functions of the other variable that it's yet to be integrated with respect to. Well, so that means this second integral may have variable limits with respect to that variable or simply constants. And lastly, dz, the outermost limits of integration, always constants, right? I mean, just so we make sense about a physical result, if you will, because these triple integrals may represent, number 1, volume, or they may represent the mass of a solid, as we will discuss later in the chapter. So it wouldn't make sense to have variables in the outermost limits of integration because, I mean, we will be getting a variable result. So we want a numerical result that represents a volume, you know. So, okay. So here's the thing. Unlike the double integrals, we had two possibilities to integrate the order dy dx or the order dx dy. When it comes to a triple integral, let's explore all the possible ways to evaluate it. For instance, so we may, if we start with dz, there's two different possibilities. That is, we go dz dy dx, which is the most common one, or at least the one we're going to go about in this class, or we may go about dz dx dy. All right? So those are two. But what if we start instead of starting dz, we start dy. So dy and dy, we have two other possibilities. It's dz dx or dx dz. All right? And furthermore, if we start with dx, we may go about dz dy or dy dz. Okay? How many possible orders of integration? A total of 6, right? For those of you who have taken statistics, how many of you have taken statistics? 119. Okay, so some of you have notions about factorials, and well, actually, those of you who took Cal 2 know about factorials, right? But what I'm trying to talk about is the combinations and permutations, right? So when you have permutations without repetition, when you use the n factorial, all right? So what is 3 factorial? 6. All right. Well, so that means because we have three variables, all right, or 3 variables or triple integral. So if we start with we have 3 to choose from to begin with, x, y, or z. If we start with z, for instance, how many choices do we have left? 2. either x and y. So that's 2. 3 times 2, 6. And then we have one more left. 3 times 2 times 1, that's 6. That's essentially the 3 factorial. Now, think about it. What if we had a quintuple integral? How many possibilities would we have? 5 factorial orders of integration. That is 5 times, so that's 6 times 4, that's 24. 24 times 5, is that 120? All right. So we would have 120 ways to evaluate a quintuple integral. Of course, yes, if you think about it, those quintuple integrals wouldn't make sense in the physical context. Like, well, the triple integral barely has any meaning, like either what's that, like the volume or the mass of the solid. Now the fourth integral really really doesn't make sense. Although those of you who are physics majors, chemistry majors, when you get to quantum mechanics or in quantum physics, you get to evaluate integrals beyond the triple, quadruple, quintuple. It's a more generalized way to describe certain physical situations. But well, that's something you're going to do later. Well, in the meantime, let's go back to Calc 3 and evaluate a triple integral. So evaluate a triple integral x, y, z squared dv, where b is the rectangular box given by this domain. In this case now, the domain will be all the order triples x, y, z, no longer the order pairs x, y, such that x is varying between 0 and 1, y is varying between 0 and 2, and lastly, z is varying between 0 and 3. So I think this one is going to be a very straightforward one. So just triple integral 0 to 1, 0 to 2, 0 to 3, x, y squared, x, y, z squared, dv. So integrate with, wait, let me iterate this. Let me go about dz, dy, dx. So the most typical order of integration in double and triple integrals, it's the descending alphabetic order, the z, the y, and then the x, unless we are asked to reverse the order one way or another, or we're trying to evaluate this integral and simply we end up at a trap where we can't integrate that function. All right, so integrating with respect z, that is the integral from 0 to 1, from 0 to 2, that's x, y, z cubed over 3, evaluated between 0 and 3. All right, and again, these limits of integration are just going to be evaluated in the variable z. That's because we integrated with respect to z. And then that's dy dx. Okay, then that's the integral from 0 to 1 and from 0 to 2. That is xy over 3 times 3 cubed minus 0 cubed. dy dx. So 3 squared, which is 27, minus 0, it's still 27, divided by 3, isn't that 9? I'm going to take that 9 outside of the integral. All right, it would be easier. It would be a lot easier. That's a 9 times the double integral from 0 to 1 and from 0 to 2, xy dy dx. And let's integrate with respect y this time. So integrating with respect to y, that's xy squared over 2 from 0 to 2 dx. Okay, and so this will be, okay, 9 halves integral from, oh wait, no more integral symbol here because we already integrated. Let me keep going here. Okay, there you go. So 0 to 1, that's x times 2 squared minus 0 squared dx. 2 squared, which is 4, 4 minus 0, that's still 4, divided by the 2 in the 9 halves, that's going to give us a 2. And then 2 times 9, isn't that 18? So 18 times the integral from 0 to 1 of x dx, which is 18 x squared over 2 from 0 to 1, which is 9x squared from 0 to 1. 9 times 1 squared minus 0 squared, that simply equals to 9. Okay? And again, the idea of this first exercise is just to illustrate how do we go about the integration, how do we still go, okay, these limits, this should go here. How do we still go one variable at a time? How do we apply the limits to a specific variable? Which one? The one we integrated with respect to it. So, and I mean, we can extend this idea to 4, 5, quintuple integrals, but of course, that's nothing we're going to do here. All right. Volume. So, did we do volume? Yes, but we did volume using double integrals. So this time we're going to define a volume integral using a triple integral, where in a similar way that we had the area integral, remember area? It's the double integral with a 1 in the integrand over the region R. In a similar way, we're going to have a 1 in the integrand for a triple integral. All right? Yes, when we get to the triple integral where the integrand it's no longer a 1, that's going to be something else that we will discuss later. Okay. So, let's have a look at one example here. Okay, use a triple integral to find the volume of the solid bounded by z equals to 2xy, z equals to 0, x varying between 0 and 2, and y varying between 0 and 3. So notice how the wording of this problem. So we're given intervals, we're also given equations. So, well, anyway, so these inequalities here, let's have a look at them. These inequalities are telling us the region of integration onto the xy plane, the projection of the solid or the floor of the solid, which we can already tell that that solid will have a rectangular base, not a square base, a rectangular base. That is a 2 by 3 rectangular base. Agree? Well, so the floor and the roof are going to be given by these two equations. I mean, how can I tell that this is the what's it called? This is the roof and this is the floor. How can I tell? I mean, without graphing the solid. Well, z equals 0. That's definitely the xy plane. I mean, think about the z values for the function 2xy. For values within the region 0, x equals 0 to x 0 to 2 and y 0 to 3, positive values. The product of positive values is going to give you positive values, so that's definitely give us a height, right? But still, if you still prefer to see the solid, let me show you GeoGebra. No, this is not the one. So open local file, okay, volume. Triple integral. Is this the one? Yes, this is the one. Actually, it's the same one we used for the average value of a function example a couple sections ago. So, again, let's have a look at the projection onto the xy plane. That is, here we can see the 0 to 2 and in the x direction, and here we can see the 0 to 3 in the y direction. That's given by the inequalities in the wording of the problem. All right. Now, what about the floor and the roof? Okay, the floor, which is actually the xy plane. Let me get rid of this surface, maybe. Is this the one? No. Let me get rid of these surfaces real quick. So that's the armor of the solid, of course, right? I have these parametric equations to create the armor of the solid here. Then, so that's the base of the solid, which is this one, right? So that's the base of the solid. That's what we obtain when we look at this what's it called? With these inequalities I highlighted with pink right here, right? Okay, so, but of course, that's the where is it? It's right here. So that's the roof, right? So that's Yeah, there's no such thing as top minus bottom. That's the XY plane. That's back to areas, right? And well, I have these walls right here just to bound the solid, right? So you can easily see the solid, okay? Put it to rotate so you can see it. Yeah, it's a little slow. I don't know why. Anyway, I'll just stop this. Okay. All right. So here we would need to, how about, I mean, why not? Just do a basic XY projection, right? Because again, it's very important to see what's going on the XY plane. So, and that's typically given by the projection of these surfaces onto the XY plane by setting them equal to 0 or something, or in some cases you will be given these inequalities to show you these regions, or to turn it into regions. Well, so volume, number one, volume equals the triple integral with a dv with a 1 in the integrand, that is over the region Q over the region D. Either way, sometimes we use letter D and Q for triple integrals, while we use R for double integrals. Well, we're ready to iterate these triple integrals. So dz, dy, dx. Okay, so let's go about limits of integration with respect to z, 0 to 2x y, and then with respect to y, we have 0 to 3 and 0 to 2 with respect to x. And I think this integral is ready to be evaluated. Okay, so that is the integral from 0 to 2 and from 0 to 3 of z, that's gonna be between 0 and 2x y, don't forget the dy dx, equals 0 to 2, 0 to 3, and that is 2xy minus 0 dy dx. However, 2xy minus 0, well, it's just 2xy, just 2xy. So the integral from 0 to 2, from 0 to 3, to xy dy dx, just integrate with respect y. Okay, integrating with respect y, so we can take that to y. The integral of 2y, isn't that y squared? From 0 to 2, that's xy squared, from 0 to 3, dx, upper limit minus lower limit, again for the variable y, in this case, because we have two at the same time. That's the integral from 0 to 2 of x times 3 squared minus 0 squared dx. So that's going to be a 9. I'm going to put the 9 outside. 0 to 2 x dx, and integrate with respect x. Come on, just general power rule. All right, that equals 9 times x squared over 2 from 0 to 2. That means 9 halves, 2 squared minus 0 squared, which is 9 halves times 4. 4 over 2, is that a 2? 2 times 9, is that 18? That equals 18 units. And well, depending on the context of a situation, it could be maybe inches cubed, maybe centimeters cubed. We don't know about it. All right? We don't know anything about it. All right.